Welcome to the Space Telescope Public Lecture Series. Today's talk, Sailing Across the Local Universe with Ulysses, a Hubble program to observe ultraviolet light from young stars, presented by Will Fischer. I am your host, Dr. Frank Summers of the Office of Public Outreach at the Space Telescope Science Institute. I'd like to note that the Space Telescope Public Lecture Series, which previously had been done in the auditorium, is now an online-only series until further notice. I also want to make great thanks to our amazing tech team, Thomas Marufu and Grant Justice, who've adapted to this online format in flying colors. Coming up next month, we have, on October 6th, we have Nancy Grace Roman and the Roman Space Telescope. We have two special speakers coming from NASA Goddard Space Flight Center, Jennifer Wiseman and Julie McHenry. And this is really cool. This is a brand new space telescope that will be launching this in this decade, and it's going to be a fun stuff to learn. On November 10th, we have Astronify, Sonification of Astronomical Data from Scott Fleming. And this is a really cool program to take astronomy data and turn it into sounds and see what we can learn from that. And then in December, Mitchell Rowalski will be talking about active galaxies. Now, I expect him to revise that title and give me something a little bit more, but hey, he's got 3 months. He'll get to it. Where are you going to find out that information? Well, you can go to our website. If you just go to stsci.edu/public-lectures, you'll find this web page with all the information on it. You can see on the left-hand side the links to our webcast, both the YouTube playlist as well as the webcast archive at the Space Telescope Science Institute. And on the right, you can see the big red button that allows you to subscribe to our emails. And of course, we send out monthly emails giving you notice of what's coming on. Each of the lectures has a link about it with the information and the abstract and a little bit more. If you go to the page for each lecture, then after it's recorded, they have a link for the webcast on the STCI webcasting, as well as down bottom, the link for the YouTube webcast. And if you would like to get reminders of all this, well, you can sign up for the announcements, as I showed you, at our website. You can also subscribe to our YouTube channel, and which is youtube.com/Hubble Space Telescope. And that will give you new video notices and reminders of live events. So you get to hear about not just our public lecture series, but also the other videos that we produce. Finally, if you have comments or questions, you can send them to publiclecture@stsci.edu. You might also want to follow our social media. We have social media accounts for the Hubble Space Telescope, for the Webb Space Telescope, and for the Space Telescope Science Institute on various media like Facebook, Twitter, YouTube, and Instagram. If you want to know what I'm thinking, every now and then I post on Facebook and Twitter. Not an awful lot, so I guarantee you will not be inundated with my tweets. However, what you will hear from me is the news from the universe, and this is the news from the universe for September 2020. Our first story tonight, studying extrasolar planets via the moon. And I put a question mark there because that doesn't sound like that really makes any sense. All right, let's start with extrasolar planets. Here is an artist's drawing of an extrasolar planet, a planet around another star. And we know of lots of these extrasolar planets, about 3,000 of them, okay? Actually, more like 4,000 if I had to correct myself. And sometimes, as you can see in this drawing, an extrasolar planet will pass in front of its star. And the light from that star will pass through the atmosphere of that extrasolar planet. So what's really cool about extrasolar planets is we can actually see what's in the atmosphere of these extrasolar planets. Here, for example, is the spectrum of one extrasolar planet called HAT P26b. And the black dots are the actual data from P26b. And the red and blue lines, those are a fit based upon what we expect to see. And you can see with the, in the middle of the graph that there's this big bump that definitely indicates a water emission line, H2O, water emission line. But on the right side, there could be a bump due to carbon dioxide or carbon monoxide that isn't really quite there in the data. So we can see the various components, and it's basically, you know, water, methane, carbon monoxide, the basic chemicals that you expect to see. And we've seen all those in various planets. We didn't see them all in P26b, but in various planets. But what we haven't seen, and one of the interesting things that we would want to see, is something that we see on Earth, ozone. Now, on Earth, the ozone layer actually absorbs a lot of the ultraviolet light. If it wasn't for the ozone layer, the ultraviolet light that gets to the ground would be much greater. You also may notice in this diagram that there is ozone at the surface, and we call that smog. Now, the ozone layer in the stratosphere forms naturally from the interaction of ultraviolet light and oxygen. So if a planet's atmosphere has oxygen, it's very likely that it's going to develop an ozone layer. So if we're looking for Earth-like planets out there, then we'd love to be able to tell, do they have an ozone layer? How are we going to find it? Because we haven't found any extrasolar planets that have an ozone layer. And actually, we're not really sure even if it's detectable. So this is where the moon comes in. Because there is one planet we know that has an ozone layer, and that's the Earth. And we can see if we can see ozone from the Earth using the moon during a lunar eclipse. So this is the geometry of a lunar eclipse, and the light is blocked by the sun, and the moon is in a total lunar eclipse. And some of the light passes through Earth's atmosphere and is refracted onto the moon. So like the light going through an extrasolar planet that we observe, here the light is coming from the sun through Earth's atmosphere, going to the moon, reflected off the moon, and we study the moon to see Earth's atmosphere. That is exactly what Hubble did. Hubble studied approximately this portion of the moon during a total solar eclipse in order to get the reflected light due to Earth. Get rid of the, take the light out that would normally come from the moon, subtract that off, and leave the reflected light of Earth's atmosphere. And the cool thing was that, yes, we were able to study the ozone in Earth's atmosphere. We were able to detect the ozone in Earth's atmosphere. And that's a really cool thing, so that if there is an ozone layer in an extrasolar planet, we've now with Hubble confirmed that we should be able to see it. And these ozone layers, as I said, probably indicative that there is oxygen and provide more evidence that the planet, the extrasolar planet that we're looking at, might be an Earth-like planet. That's kind of cool. Our second story for you tonight is Hubble's view of comet Neowise. Now, you may remember back in July, we talked about comet Neowise. And I showed lots of pictures like this, comet Neowise sitting in the sky. I hope some of you were able to go out there and look at it with binoculars and see it, because it's very rare that you get a good naked eye comet. And of course, Hubble is going to take a look at it, but this is a wide field view. This is 50 degrees wide. Hubble doesn't have quite that field of view. Matter of fact, Hubble's field of view is really small. So if we zoom in to that wide field picture, and then we zoom in again to that picture, that pullout, take a couple levels of zoom, you can see the tiny, tiny field of view that Hubble has. So Hubble isn't seeing the big long tail. That's not what Hubble does. Hubble looks right in at the nucleus of a comet, and it's looking at the details right in the very center, the giant snowball where the ices are evaporating away and then being blown back into the tail. And so this is Hubble's view of the nucleus. And even Hubble doesn't resolve the nucleus, okay? It's still unresolved in that white dot there in the center, but you can see that there's an asymmetric spray of stuff coming out of it. Matter of fact, Hubble actually saw a jet of material and the comet rotating. It took a couple pictures, and here are two of them in an animated GIF, where you can see that the jet that's spewing this material is rotating between the images. So the comet nucleus is rotating and there's a jet that's spewing out material, and Hubble can actually see the rotation of that jet. So while Hubble isn't going to give you these gorgeous pictures in a wide field with a big long comet tail, Hubble will be able to get you the details. And for the scientists, all of the really cool stuff that we want to understand about it really does happen right down in that nucleus. So Hubble can give us that and complement these gorgeous images that I showed you back in July. All right, that's it for our news from the universe. We're now going to go to our featured speaker. And I will switch over to him. Our featured speaker is Will Fischer from the Space Telescope Science Institute. He has been at the Space Telescope for 4 years. He's an STSCI scientist on the COST team, where he provides user support. So all the astronomers who want to use the cosmic origin spectrograph, he's the kind of guy who goes in and helps them get the best out of their data. That's one of the reasons Hubble is so productive, is that we got this great team that helps users of the telescope get the most out of their data. Before, he's been here for about 4 years, and before that he did some postdocs at the Goddard Space Flight Center and at the University of Toledo. He got his PhD at the University of Massachusetts. And I asked him, you know, what's one of the interesting things that happened to you during your astronomy career? And he told me about this time when he was going up to do observing on at the telescope. And it was Thanksgiving, but they had to get up to the telescope, so they couldn't go out for a normal Thanksgiving dinner. And he and his advisor ended up having Thanksgiving dinner at a gas station. All right, so this is what you do. You sacrifice for your science. Ladies and gentlemen, Dr. Will Fischer.
Well, thanks for coming, everyone, and for bearing with us in this online kind of unusual format. So today I'm going to be telling you about our program called ULLYSES that we're doing with Hubble. And it's a program to observe ultraviolet light from young stars. So I'm going to start off by telling you about what all that means exactly. ULLYSES is an acronym. You notice it's maybe spelled a little bit different from the hero Ulysses of mythology. It stands for the Ultraviolet Legacy Library of Young Stars as Essential Standards. And what this is a Hubble program to observe young stars in the Milky Way and nearby galaxies as well. Now, your average Hubble observing program works in the following way. It's led by one or more astronomers who put in a proposal, and the proposal was compared to proposals from astronomers all over the world, and the best ones get time. We at Space Telescope help these astronomers use their telescope time efficiently and help them make the most of their data. And when the data come in, only the primary investigator and their team can access the data at first. ULLYSES is different. The staff at the Institute plan and implement it, not just on our own, but with input from the worldwide scientific community. All the data go public immediately, so there's no delay. And this is similar to other programs you might have heard of before, like the Hubble Deep Field that was observed, closer to the beginning of Hubble's mission, or the frontier fields. And this is an approach that we use sometime for major investments of observing time that appeal to broad segments of the community, but maybe are just larger chunks of time than any one investigator is likely to get on their own. So those are just the basics of ULLYSES, but to give you the context for all this, we're going to kind of go back a few hundred years when astronomy was a very different discipline, and give you a little bit of history to find out how we got to ULLYSES today. So in the early days of astronomy, before the 19th century, astronomers focused mainly on mapping stars, looking at their brightnesses and positions, and then figuring out the nature of the solar system and how the solar system is arranged. But nobody had any idea what celestial objects were made of. Here I'm showing you an image of Orion and Taurus and some of the winter constellations, a map drawn by hand by Flamsteed in his celestial atlas. And you can see a lot of the figures that were drawn to accompany the stars and give you a sense for the mythology that was going on in the sky. At about the same, or at similar times in history, Copernicus made worked with careful observations of the solar system to figure out how the planets were arranged. For millennia, people had thought Earth was at the center of the solar system, but Copernicus put forward his heliocentric model of the sun being at the center and the planets in the order that we're aware of today, with the moon orbiting Earth. You'll notice in this diagram, Saturn is the last planet, and then beyond that, there's kind of a fixed sphere of stars. So, the solar system was figured out in a lot of detail, but people didn't really understand what the stars were. There's another image here showing Galileo's sketches of Jupiter's moons. Galileo was the first astronomer to use a telescope to study the sky, and he discovered that Jupiter had moons, and their positions changed with respect to Jupiter and with respect to each other from night to night. So lots of important work was being done, but there was still no understanding of the stars and planets as real objects that one could conceivably go to and study in detail, given the right technology. At the same time, physicists were making progress in understanding what light was. Here's a little cartoon of Newton passing white light, passing sunlight through a prism. The prism spread that light out into its colors. So instead of just being one single thing, light was in some sense made up of different forms of light, light with different colors and different energies. So this was maybe the very beginning of applying physics to light that we could receive from the sky. And this spectrum that Newton made with his prism will be an important feature later on in our talk. In 1835, Auguste Comte, who for the most part was a really good philosopher of science, he made a lot of contributions to understanding what we do when we do science and the nature of scientific inquiry. But he said something unfortunate in 1835. He said, "I persist in the opinion that every notion of the true mean temperatures of stars will necessarily always be concealed from us." And he had similar things to say about not just the temperature of the stars, but their chemical makeup. Now, this turned out to be a pretty bad prediction. At just about the same time, Joseph von Fraunhofer was studying the spectrum of the sun in more detail than Newton had. And in this image that we see here, he's studying a spectrum, and this is a German postage stamp commemorating Fraunhofer's discovery. He found that in the spectrum of the sun, it wasn't just a continuous spectrum, but it had this array of dark lines in it. And it took a while to determine what those dark lines were. By the 1860s, Gustav Kirchhoff had explained the origin of these spectral lines. And even today, physics students learn about Kirchhoff's laws. Here we have what's labeled a hot black body. That's kind of a physics name for a star, just something that's radiating a lot at all wavelengths. If you pass that light through a prism, you might get a continuous spectrum, like you see in the lower left corner of this image. But if that light passes through a cloud of cooler gas, then the materials, the chemical elements or molecules in that gas will absorb out certain lines in the spectrum. So you get this pattern of dark lines that depends on what's actually in that gas. When we take a spectrum of a star, we're really, think of the cloud of cooler gas in this case as the outermost layers of the star's atmosphere. So that starlight is passing through the outermost parts of the star, and that gas absorbs out these narrow lines. And it was determined that the lines in the solar spectrum corresponded to the patterns of lines that you could observe on Earth if you passed light through gases in a chemical laboratory here on Earth. If you look at just the gas without the source behind it, then instead of absorption lines, you see emission lines in exactly the same pattern as the absorption lines. So this gave scientists the idea that they could look at these spectra and start to understand what the stars were made of, and to learn something about their temperatures and motions in the stars and near the stars. This is a modern spectrum of the sun obtained from the McMath Pierce Solar Telescope up at the Kitt Peak Observatory in Arizona. And you can see how much detail is available to modern spectroscopists. You can really spread that starlight out into the familiar colors of the spectrum, and you can see just how many absorption lines there are in this spectrum. There's just forests of lines from all sorts of different materials that are in the solar atmosphere. So our study of the sun has really been advanced thanks to spectroscopy, and we can apply these same insights to other stars as well if we have instruments that are sensitive enough. So let's talk about some of the things we can learn from a spectrum in more detail. If you read the advertisement from this talk, you would have seen words like a picture is worth 1,000 words, but a spectrum is worth 1,000 pictures. It can reveal things about an object's composition, like we were discussing, its temperature, also its density and its velocity, how things are moving, in what direction and how fast. This is just a little schematic showing how astronomers make a spectrum. We pass light from a star through a telescope. That starlight is fed maybe through a fiber optic cable of some kind, or maybe not, but it eventually reaches a grating, which is sort of like the prism that Newton used. The details are a little bit different, but it breaks the light up into its component colors, and we record that spectrum on a detector. And you can see here the little cartoon of the rainbow-like spectrum with all the different absorption lines in it. In practice, astronomers look at something a little bit different when we actually study a spectrum, and we'll get more into that later. So what about composition can we learn from a spectrum? We've talked about these different patterns that you get from different elements, and this is a picture showing many elements from the periodic table and all of their signature emission lines. So you can see like hydrogen up in the upper left corner has a pretty simple spectrum with just a few bright lines, but some of the other elements are much more complicated. Iron, for example, over here in the upper right has this wealth of emission lines all across the spectrum, and it gives astrophysicists a real challenge in trying to figure out physical conditions from this whole forest of iron lines. And just as an example of how we use spectra to study chemical composition, here I've got an image from Hubble of a nebula that's pink in color. And a lot of the nebulae that you see in Hubble images have this characteristic pink color. And that's due to that bright red emission line from hydrogen that you can see in the diagram here. And you've got contributions from other gases as well, but it's mostly hydrogen. This is a little web tool I came across where you can actually click on different elements in the periodic table and look at their spectra, maybe a little in more detail than we had before. So here's the spectrum of hydrogen with that bright red line and a few other lines in the blue and toward the purple. Oxygen is pretty interesting. Those bright green lines that you see there are what give color to the aurora borealis. They're a major contribution to the aurora. We all know about neon signs. If you look at the spectrum of neon, you can see why they have that characteristic orange color. Or if you see a blue sign and call it a neon sign, maybe xenon is actually what's giving it its color. And again, here's the spectrum of iron with all those lines. So there's lots of diversity, and if you have multiple different contributions to a spectrum, it can be a little bit of a puzzle to figure out what lines go with what element or what molecule. So what are the stars themselves made of? This is kind of an interesting story in astronomy. Astronomers initially saw lines in the solar spectrum of carbon and silicon and other common elements of Earth that we see here on Earth. And they assumed that the sun must have the same composition as Earth, only hot enough for everything to be glowing. It's a reasonable assumption to start with. But in 1925, Cecilia Payne, who was one of possibly the first American woman to get a PhD in astronomy, concluded from spectral analysis that the sun was actually made of hydrogen for the most part. This was very controversial. None of the big wigs in astronomy at the time believed her, but she turned out to be right. And today we know that stars in our galaxy are around 70% hydrogen, 25% helium, and a few percent everything else altogether. Astronomers have this habit of referring to the everything else as metals, even things like oxygen and carbon, which are clearly not metals according to anybody, a chemist's definition. But we just use that as a shorthand to mean everything except hydrogen and helium. And as if you look at stars that are in other galaxies further across the universe, you find stars with different metallicities, different fractions of these heavy elements compared to what we see in the sun. So that'll become important again when we talk about Ulysses in more detail. So temperature is another thing we can learn from a spectrum. These are stacked spectra from several different stars, and they've been placed in an order that depends on their temperatures. And you see this column of letters and numbers over to the right. This is a system we use to classify the spectra of stars by their temperatures. The O stars are the hottest. The M stars are the coolest. And those numbers that you see next to the letters are subclasses. They give you a little bit finer information than just the letters themselves. The reason the letters come in that order is that they were actually first placed in order by the strength of their hydrogen lines in their spectra. The A stars have the strongest hydrogen lines. So if you've been looking at this diagram for the better portion of a minute now, you might realize that this strong line about a third of the way from the left is a hydrogen line. And you can see how it's really strong in the A stars, and there's not much else in those stars. As you go to hotter stars, the B stars have the second strongest hydrogen lines. But then when you go to the O stars, that was toward the end of the alphabet. So when people were first doing this classification, they placed the O stars toward the end because the hydrogen lines were so weak. But they're weak because those stars are so hot. The way the hydrogen atoms emit changes as you get to those very high temperatures. The G, K, and M stars are much cooler. The hydrogen lines get weak, and then you start to see many, many lines due to what astronomers call metals. The sun, by the way, has type G2, so its spectrum is kind of between the G0 and the G5 that you see here. So the temperature of the star tells us what kinds of lines you see, but it also tells us, it's also related to whether the star is blue or red or somewhere in between in appearance. So we're going to look at this stellar temperature simulator. So what we're looking at here is a plot of something related to the star's brightness. They call it spectral power density, but that's really just how bright the star is as a function of wavelength. And the rainbow shown here shows you the red, orange, yellow, green, blue, and violet that our eyes see. So what we're looking at here is roughly the spectrum of the sun, although without any of those absorption lines. And you can see it peaks at visible wavelengths. The reason those wavelengths of light are visible is because the eyes of animals and humans evolved to detect light that was plentiful from the sun. But if we change our temperature over here on the slider, if we first go to cooler temperatures, for one thing, the star gets fainter. And for another thing, that peak emission starts to go to longer and longer wavelengths. You'll notice now we're down to about 4,000 Kelvin, which is roughly 8,000 degrees Fahrenheit. You could work it out exactly, but multiplying by 2 gets you pretty close. And now for these relatively cool stars, the spectrum's peaking at red wavelengths, and there's a lot of light being emitted out at longer wavelengths even than we can see. And we can keep going cooler and cooler until the star gets quite faint and quite red. Now let's start going to larger temperatures. We're back to the sun. And now we very quickly start to run off the top of the plot. So let's look at a little bit more of it. Let's kind of zoom out. And now as we're getting hotter and hotter, look at how that peak goes even past the violet into the ultraviolet. And you can see how hot stars are emitting most of their energy there. And to our eyes, they start to appear blue because most of the visible light is coming out in blue colors. So this discovery of the relationship between the temperature of a star and its color was very important in helping astronomers to start making headway on understanding stellar evolution. How stars change as they go through what we think of as a life cycle. Oh, what about density? Here are some spectra obtained long ago of different stars, and they've all got strong hydrogen lines, but the hydrogen lines look a little bit different from one star to the next. The one labeled HR 1040, that's a very luminous, large, giant star. And these giant stars have low density. What this means is that the atoms and ions in the star itself are moving around relative to each other, not so fast because the density is low. So you get these narrow lines. But in the higher density, we call them dwarf stars. They're not really like tiny stars, but they're much smaller than the giants. There, the pressure in the outer layers of the star's atmosphere is quite a bit larger, and that causes the lines to broaden. So you can look at the width of a spectral line and learn something about the density of the material that's responsible for it. We can also learn about velocity. Now, I'm showing a stock image of a MARC train here because it's relevant, but also because in this work from home environment, I kind of miss taking the MARC train back and forth to Baltimore every day. But the reason it's relevant for this is if you just think about the whistles that trains make, you can hear from miles away sometimes. If a train is moving toward you, the pitch of the train whistle increases. It's almost like the sound waves are getting smushed together and start to take on a higher pitch. As that train passes and then moves away from you, the pitch of the sound gets lower and lower. Light does that too. We call it the Doppler shift. And when a star is moving away from us, its lines can be redshifted. They shift to longer, redder wavelengths. If a star or something near the star is moving toward us, then you see a blue shift and the lines go to shorter wavelengths. So velocity is an important thing that we learn from spectra as well. So putting together some of the things we can learn from stellar spectra, one thing we've come to know is that stars differ greatly from one another. They have an enormous range of luminosities and surface temperatures. Now, luminosity, you probably realize that that word has something to do with the total energy output from the star, how bright it is. It's related to its size and its temperature, and it varies incredibly from star to star. In this schematic diagram here, you can see a red dwarf star. Its luminosity is less than 1% of the sun's. These are very small stars that burn their nuclear fuel very efficiently, and they exist they'll exist for much longer than the current age of the universe. Then you have the sun, which is kind of a typical middle-sized, maybe a little bit above average size star. But the giants and supergiants are the most luminous stars. A blue-white supergiant star can have a luminosity up to 1,000,000 times that of the sun. And these stars burn through their fuel really quickly as far as stars go, and may only exist for 10 million years before they go supernova. Surface temperatures also vary a lot. For the red stars, the surface temperature is maybe 5,000 degrees Fahrenheit. The sun's about 10,000 degrees at its surface, and these hot blue stars can be 70,000 degrees or more at their surfaces. So there's this whole zoo of different stellar types. And astronomers and spectroscopists want to study all of them to understand what else changes about the stars besides their luminosities and temperatures. So to make sense of all this, around 1910, the astronomers Hertzsprung and Russell plotted the luminosities and temperatures of stars on the same diagram. They put temperature in reverse, and astronomers continue to do that today with hot blue stars at the left and cool red stars at the right. And what they notice is that most of the stars that they observed appeared on this diagonal line that goes from upper left to lower right, more or less. This was named the main sequence. And as the theoretical understanding of stellar evolution came along, people realized that stars move through what we call the HR diagram over their life cycles. The reason so many stars are on the main sequence is because that's where stars spend most of their time. And the path of a star through the main sequence, it varies from star to star, and it depends mostly on the star's mass. This is a different HR diagram. It doesn't show any actual stars except the sun, but it shows the paths that stars of different masses take through the HR diagram. All of these paths here show how what these stars do early in their life cycles before they reach the main sequence. Ulysses is studying both kinds of stars, massive and low mass stars, about 50-50 between the two. Low mass young stars, like you can see here for the 1 solar mass and half solar mass star, most of their movement before they reach the main sequence is vertical. They stay at roughly the same temperature, but they get less luminous. What's actually happening is that they start kind of large and diffuse, and as time goes on, gravity pulls them together to make a more compact object, eventually reaching something the size of the sun, or like one of those red dwarf stars if it's less massive. And it takes them a few million years to do this. But then once they reach the main sequence, they stay there for billions or perhaps even trillions of years for some of the least massive stars. These high mass stars labeled 9 and 5 solar masses, they mostly move horizontally across the HR diagram as they form. And these stars, everything they do quickly, at least for stars. They reach the main sequence almost immediately in star terms, and they might spend only a few million years on the main sequence before evolving past that. So one of the challenges for the high mass stars in Ulysses is to really get a good sample of stars at all these different places in the HR diagrams, because high mass stars are tricky, and it's difficult to predict what any given star is going to do next. So I want to talk a little bit more about the light that we get from stars. I've alluded to this a few times in the talk so far, but beyond the visible parts of the spectrum, there's evidence for radiation that can't be seen. And this was figured out not too long after people started passing light through prisms. The ultraviolet rays are beyond violet. That's kind of what ultraviolet means. They were detected from the effect that they had on the photographic technology of the time. These UV rays would develop photographic paper even more quickly than violet rays themselves. So people knew there was definitely radiation there, even if they couldn't see it. Infrared rays were detected from their effect on thermometers. Infrared radiation would heat up thermometers just like red light would. So this is how ultraviolet and infrared radiation came to be known. And then there are also other well-known kinds of electromagnetic radiation. You've probably heard of X-rays, radio waves, gamma rays are another. And these are all fundamentally the same thing, just at different energies, only a small range of which can we see with our eyes. So this little schematic shows what happens to the different types of electromagnetic radiation as they reach Earth's atmosphere. Visible light makes it all the way through to the ground, unless it's cloudy. It's frustrating that with all the technology we have, after all these years, astronomers still can't do anything about a cloudy night if they're observing from the ground anyway. But without clouds, that visible light makes it all the way through to our observatories. And UV light that's just a little bit beyond visible and infrared light that's just a little bit beyond visible can also make it through. As you go further into the infrared, you reach a point where the radiation, this is kind of the mid-infrared, doesn't quite reach the ground, but it does reach into the stratosphere. So we can use telescopes on planes. For example, SOFIA, the Stratospheric Observatory for Infrared Astronomy, is a plane that takes off many nights a year and goes up to 40,000 feet and detects infrared radiation. As you get into the far infrared, you really need space telescopes like the Spitzer and Herschel space telescopes that did their work in recent decades. At very long wavelengths, you start to get into millimeter and radio waves that do reach through to the ground. And at very long wavelengths, that's no longer the case. Going shortward of the visible, the ultraviolet gets through the atmosphere to some extent, but then as you get to longer X-rays and gamma rays, light no longer penetrates Earth's atmosphere and you need space telescopes. So Ulysses is detecting optical light as well, but it's really centered on ultraviolet spectroscopy. To measure ultraviolet wavelengths, we use a unit called the angstrom. It's not part of the international system of units, and some physicists find this annoying that astronomers use something that's not officially part of the system. But an angstrom is 1/10,000,000th of a meter. So pretty tiny. And the ultraviolet extends from the extreme ultraviolet at 100 angstroms out to the near ultraviolet, which is almost visible at 4,000 angstroms. In this UV radiation, it traces things that are hot. If you remember when we looked at the broad spectrum of a blue star, a lot of that light was actually coming out in the UV. So the hot stars eliminate or give off a lot of UV light. It also traces energetic processes. Low mass stars may have energetic things happening just above their surfaces that give off UV emission. So they can be interesting UV targets as well. Well, as I was saying, to study ultraviolet light, we really have to go above the atmosphere. There are lots of different space telescopes, and there have been ultraviolet telescopes before Hubble, but at the present time, Hubble is really the only way to do sensitive ultraviolet spectroscopy. It's not possible from the ground and from space. It's really just Hubble right now. There are alternatives in the works, but the most promising of those, we're really waiting until the mid-2030s to have anything that approaches Hubble's capabilities for UV spectroscopy. So even here in this, 30 years into Hubble, it's important to really make good use of its ultraviolet spectroscopy capabilities to do science. Now, many of you probably know Hubble has multiple instruments. It's got Wide Field Camera 3 and the Advanced Camera for Surveys that do a lot of imaging. But 2 of Hubble's instruments have UV are able to do UV spectroscopy. And we're leaning on these heavily for Ulysses. These are STIS and COS. STIS is the Space Telescope Imaging Spectrograph. This picture shows astronauts installing STIS in 1997. And one of the real advantages to Hubble compared to other space telescopes is it's in low Earth orbit. So it's been possible 5 times in its history for astronauts to go up and repair it and install new instruments. That's the major contributor to its 30-year lifetime. A lot of other space telescopes have enabled all sorts of wonderful science, but they're limited, for mechanical reasons, limited in some way to operational lifetimes of 5, 10, 15 years. Well, the advantage to STIS is not only is it a UV spectrograph, but it can also obtain optical spectra and infrared out a little bit into the IR, what we might call the very near infrared. And it has a lot of different modes that enable you to obtain different types of spectra depending on what you're trying to learn about your target of interest. So the best word for STIS is versatile. Our other instrument, COS, that's a little bit newer than STIS. It was installed in 2009 in the final servicing mission. It obtains only ultraviolet spectra. It has a far ultraviolet channel and a near ultraviolet channel, but at higher sensitivity than STIS. So if you have focused ultraviolet spectroscopy needs, often COS will be the ideal way to go. And like we mentioned at the start of the talk, I'm on the COS team at the Institute. All of the active Hubble instruments have teams of scientists and engineers who work together to keep the instruments well calibrated. We have lots of interesting ways of doing that, given that the instruments are all in low Earth orbit and we can't go tinker with them. And we also have to support users to help users of Hubble, people who get Hubble time, make the best use of their data. So the Ulysses project, we talked about this a little at the beginning, but that's starting to have been a while ago. So I'll remind you, we use what's called director's discretionary time. This was used in the past for programs like the Hubble Deep Field and the Frontier Fields. Ulysses is going to be about 1,000 orbits. Unlike other observatories, Hubble measures its time not in hours, but in orbits. And an orbit gives you 50 to 60 minutes of observing time, depending on where precisely you're looking in the sky. Half of the orbits are for massive stars, half of them are for low mass stars. And the thing about astronomers, we like to specialize. So it's very different communities of research that specialize in each of these subfields. The data are immediately available to the public. So if you were interested in high mass stars, you could go see which one Hubble was looking at this past week and go get the data right away. And our staff play a lot of different roles in Ulysses, choosing targets, setting up the Hubble observations, and making the data available to the community in useful ways. So I just wanted to show you our team that's implementing Ulysses here at Space Telescope. Julia Roman Duval is the leader of the implementation team, and Joe Taylor leads the data products effort. That's sort of what we do with the data after it's obtained to make it available to the public. Charles Prophet is the observing lead, so he leads the efforts to implement the observations and get everything set up for the telescope. Tala Monroe helps him with that. And then we've got a whole staff of people that help with different aspects of implementation and data products availability. I'm sort of leading up the scientific expertise for the low mass young stars. Alex Fullerton handles the high mass young stars. And it's really just a coordinated effort that crosses different instrument teams and extends into the Office of Public Outreach. Lots of different people are involved here. And we've got extensive involvement from the broader community as well. There was this whole thing started with a committee of 10 astronomers from Europe, Asia, and North America that sort of defined the broad goals of the program and told us what to do with our time, roughly speaking. There was a call where astronomers from anywhere around the world could propose targets as part of Ulysses, low mass and high mass stars. We've got a science advisory committee of 8 astronomers who give us input on the work we're doing and help us resolve issues on the fly when scientific expertise is needed. And we've got huge international teams of dozens of astronomers who are, getting funded to analyze some of the Ulysses data and to get complementary data from other observatories. We've got some snapshots here of some of the ground-based and space-based telescopes we'll be using alongside Hubble. NASA's infrared telescope facility. That's the one that I was on the way to when I had to have Thanksgiving dinner at a gas station that one time. There's Europe's very large telescope facility, which is actually in Chile, but just administered and operated by the Europeans. And NASA's Chandra X-ray Observatory, which has been up in space measuring X-rays from the sky for a long time now. One aspect of Ulysses that I've been spending a lot of time on this past week is this ground-based observing with this robotic global telescope network, which is kind of interesting to see in operation. This world map here shows you where this Las Cumbres Global Observatory has all of its observing sites, and these aren't really big telescopes necessarily, but there's a lot of them, and they're well positioned, so as Earth rotates, different telescopes are always available to look at the night sky. And we're using these to get some data about the low mass stars to put their ultraviolet observations in context. These stars are highly variable. So we want to observe them over and over again, understand how their brightness is changing. Both, if one of them were to suddenly get much brighter, it could damage COS or STIS. So we want to prevent against that. But this also gives us good scientific input to understand what these stars are up to when we look at them with Hubble. And I've just kind of got some snapshots here of some of the relatively small 0.4 meter telescopes that we're using to support Ulysses. So now onto the ultraviolet spectroscopy that's at the heart of Ulysses. So why do we want to do ultraviolet spectroscopy of young stars anyway? Well, I've got an image here from Hubble of the Orion Nebula. And Orion is really important to astronomers who study star formation. It's the closest star-forming region to Earth that has both massive and low-mass stars in large quantities. The most massive stars in the Orion Nebula are the trapezium in the center and shown in this relatively large inset here. These are O and B stars, like I was talking about a while back. And the radiation from these stars, which is mostly in the UV, impacts everything else that's going on in the nebula. So they really control the evolution of the Orion Nebula and the low mass stars within it. These smaller insets show you detailed close-ups of some of the low mass stars. And not all low mass young stars are like this, but the ones in Orion have these kind of very carefully shaped nebulae associated with them, as the UV light from those massive stars kind of shapes the environments of the stars. And then UV observations of the low mass stars themselves reveal high energy processes. These stars are still forming, and that gives off a lot of energy, and it has a strong ultraviolet signature. So first, I'll talk a little bit more about the massive stars. The targets that we're observing with Ulysses that are massive are actually in other galaxies. O and B type stars in the Milky Way are often too close and too bright to observe safely with COS and in STIS's UV modes. So the massive stars we're looking at, most of them are in the large and small Magellanic Clouds, which are a few 100,000 light years away. A few of them are in these somewhat more distant galaxies, still nearby as far as galaxies go, but they're 4 to 5 million light years away, Sextans A and NGC 3109. An advantage to these galaxies is that the stars in them have fewer of those metals, anything heavier than helium relative to the stars in our galaxy. So we can learn something about how stars operate and how stellar evolution proceeds at what we call low metallicity. These are images from ESO, the European Southern Observatory, and Hubble of the 4 galaxies that have Ulysses massive stars in them. And you notice all of these galaxies are a little bit fuzzy and not quite as well organized as the grand spirals that you see in the Milky Way galaxy or the Andromeda galaxy. So, this tells us something about how stars evolve in less massive galaxies. Some sites of star formation in the Magellanic Clouds are much more active than those in our own galaxy. So again, by observing stars in other galaxies, we can sort of understand the full spectrum of star formation beyond just what you would see by looking at Orion or other regions in our own galaxy. This is a Hubble image of part of the Tarantula Nebula in the Large Magellanic Cloud. Some of our Ulysses targets are in the vicinity of this region. You can just look at how many hot, bright blue stars there are packed into a fairly small region of space. And again, the radiation from these stars really impacts the entire star-forming region. This is the Hubble 30th anniversary image, which some of you may have seen in recent months. And it's a really excellent image just for its own sake. It's got this giant red nebula in the Large Magellanic Cloud and this smaller blue nebula next to it. But we notice that one of our Ulysses targets is actually in it. This SK-67167 circled there is one of the massive Ulysses stars, and we'll have a spectrum of it. And we like to use this to emphasize that Hubble's spectroscopic investigations are just as important and just as interesting as its imaging observations. So we're about to look at a spectrum of a hot star, and I just wanted to point out that when astronomers analyze spectra, we tend not to look at these kind of rainbow light plots with dark lines in them. We instead show how the intensity changes as a function of wavelength. So we'll look at a line like you see here, where you have dips of different depths and widths for different absorption lines, or possibly the reverse for emission lines. This is the spectrum of a hot star, about 20,000 degrees Fahrenheit, an A-type star that's predominantly hydrogen. And below that, there's a spectrum of a sun-like star with about the 10,000 degree temperature of our own sun, and many absorption lines due to metals in its atmosphere. So this is a UV spectrum from COS of a massive star. And you can see that there are lots of absorption lines here, a few things that start to look like emission lines. And here are highlighted some lines that are labeled as ISM, this is a magnesium line, stellar wind, and CGM. ISM and CGM are the interstellar medium and the circumgalactic medium. And so that points to the fact that these spectra tell you not just about the star, but about interstellar matter and intergalactic matter that lies between us and the star. So this diagram shows how as light from a star passes through different clouds of gas on the way to Earth, those clouds can impart absorption lines on the spectrum. So in addition to broad stellar lines, you might see narrow lines due to the clouds, and you can learn something about the composition of what you might otherwise have thought to be empty space. So massive stars are very useful in that sense. But the spectra also tell us a lot about the stars themselves. This is a Hubble image of the hot star Eta Carinae. It has this really intense stellar wind. It's one of the most highly variable stars in the sky, a bright source of UV light that unfortunately is too bright for Hubble, but it's a great example of a stellar wind. When you see gas in front of a star, it gives us absorption lines, just like at the beginning of the talk I was telling you about Kirchhoff's laws. So you can see these broad absorption lines from all that gas in front of us, and then they're blue shifted because the gas is moving toward us. So this tells us something about the velocity and the density structure of that stellar wind, which ultimately is what's carving away the nebulosity in the star forming region and affecting the low mass young stars. Now we're going to switch gears a little bit and talk about the low mass stars themselves. The low mass stars observed by Ulysses are nearby as far as stars go. They're hundreds or even just dozens of light years away, as opposed to those massive stars, which were in some cases millions of light years away. They're located in or very near dark clouds, which are exactly what you would expect from their name. They're regions of gas and dust that are dense and therefore dark compared to space in general. This is the stuff that's going on to form new stars. And there are a couple images here of the dark clouds, Chameleon 1 and Lupus 3. They get those names because of the constellations they're in. So the Ulysses low mass stars are also known as T Tauri stars. This is an image of T Tauri itself. It's not a Ulysses target, but it gives its name to the class of stars that we're studying with Ulysses. And the name of this star means that it's a variable star. The single letter T means that it was one of the first variable stars to be discovered in the constellation Taurus, which is where you get the name Tauri. So the T Tauri stars, it was eventually realized, have masses similar to the sun's, but instead of being a few billion years old like the sun, they're only a few million years old. They're basically the unpredictable teenagers of low mass stellar evolution. They're still building up mass, although not as quickly as they were when they were infants. They're subject to unpredictable outbursts at times as they accrete matter and emit some of it. And since mass determines how a star evolves, these are windows into the early days of our own solar system. We can get a great sense for what the sun and potentially its planets were up to only a million years after they formed. Here's a little schematic of how low mass star formation works. In those molecular clouds I was showing you, some portions of those clouds are much denser than average. And once you get enough material in one place, it starts to collapse under its own gravity. So you'll have collapse into what we call a protostellar envelope. Eventually, something we call a protostar forms in the center of that envelope. It has a disk forming around it, and jets emitted from the star start to blow away parts of that envelope around the poles. So if you're looking at it from just the right angle, you can start to see the protostar. And James Webb is going to be really useful for helping to understand what these protostars are up to. Ulysses is focused on slightly more evolved stars where that envelope is gone and you're left with a star and a disk and probably planets forming in the disk. After about 2 million years, or maybe a few million more years, depending on the star and fine details of the situation, even that disk is gone and you're left with the sun and planets. And we know that T Tauri stars are forming planets. This is an artist's conception of the ALMA Observatory in Chile. It's an array of telescopes way up high in the Atacama Desert, one of the driest places on Earth, and it detects millimeter wave radiation. So almost as low energy as radio waves, but not quite. As an array, ALMA works as though it were one giant telescope. It doesn't have the sensitivity of a huge telescope that covers as much ground, but it's got the right angular resolution, so it can make really finely detailed images. And this is an image of HL Tauri, which, like T Tauri, is in the constellation Taurus in a variable young star. And in this image of the disk, you can see all this structure. This came out just about 5 years ago, and everybody was just amazed to see all these gaps and rings in a disk. We don't have direct evidence for planets in all disks like this, but those gaps and rings are pretty good indirect evidence that planets are forming. Now, Ulysses is not going to study the details in these disks. It studies what's going on near the star. This is the UV invisible spectrum of a T Tauri star, similar to what we'll be getting with Ulysses. So there's a lot going on here. I want to try to explain it all. We refer to the flattish part of the spectrum that changes slowly with wavelength as the continuum. And then we have all these bright emission lines on top of it. In this image, the red and the green correspond to visible light. These will be observed with STIS. And in T Tauri stars, that visible light is mostly coming from the star itself. As you go into shorter wavelengths, the UV continuum, the purple and blue that we'll be observing with STIS and then with COS at the shortest wavelengths, the continuum that's available there is mostly coming from accretion processes. As matter goes from the disk onto the star and comes to a sudden stop on the star, it emits a ton of energy, and that's what gives you the UV continuum. And then all of these emission lines that you see at all these wavelengths are also due to accretion. And in some cases, the small fraction of material that's being ejected from the star. And these smaller plots here show you how some of the far ultraviolet lines look if you really zoom in on them. From the structure of those lines, you can learn a lot about how material is moving just above the surface of the star. Now, all of these T Tauri stars are accreting mass at variable rates. And one of the goals of Ulysses is to study stars with a range of masses and accretion rates, so we can understand how the star formation process depends on those factors. Whether massive stars form more quickly than low mass stars, and just other aspects of the star formation process. So from years of studying spectra like this in UV and optical and infrared wavelengths of T Tauri stars, X-rays as well, astronomers have been able to put together this little schematic of how accretion works in low mass young stars. And for me, one of the most exciting things about astronomy is you can start with pretty indirect evidence, like a spectrum, and through detailed study and theoretical modeling, construct a highly detailed picture of what's going on in regions that are still far too small to detect directly with an imager. So in this T Tauri star, there's material in its disk from just when it began to form. Some of that material is forming planets. And as you can see here, ALMA probes the outer disk. But then over time, material in the disk drifts inward. Once it gets to the innermost part of the disk, which is what James Webb will excel in studying, it can't get any closer to the star by continuing to move toward the star's equator. The reason is that the star has a magnetic field. This is another one of these things that we can study from spectra that I haven't gone into much detail tonight, but you can learn about a star's magnetic field from its spectra. So this disk material is encountering resistance from the star's magnetic field, and it has a much easier time flowing along the star's magnetic field lines, where it then crashes into the star far from its equator, closer to the poles. So all this gas in what we call this magnetospheric flow is moving at high speeds and low density, and it's what gives us a lot of the emission lines that we see in UV and optical spectra. And then this heated region on the stellar surface, the star itself is maybe 4,000 Kelvin. This accretion region gets much hotter, 8,000 Kelvin or even hotter than that, directly underneath the accreting material. So that radiation gives us the UV continuum and even contributes to the X-rays. So Hubble, through Ulysses, is telling us how the accretion process works in T Tauri stars with a broad range of masses and accretion rates. So here's the timeline for Ulysses and our logo that was artfully contributed by the Office of Public Outreach. About 30 of 169 of the 169 massive stars have already been observed. Even in these other galaxies, the massive stars are fairly bright, and it's easy to observe a lot of them with the amount of observing time we have allocated. So that's already underway. Observations of the low mass stars are going to get started in November. Because these low mass stars are so variable, there's all sorts of coordinated observing going on. And in November, there will be windows where we can observe the stars at the same time with TESS, which is another orbiting telescope. So the T Tauri stars, the low mass stars, there are two samples. There's a small monitoring sample of just 4 stars that are going to be observed over and over again to see how their UV spectra change with time. And then there's a much larger survey sample that will be observed one time each to see how the spectra depend on the masses of the different stars in the survey sample and their accretion rates. Observations are going to be continuing through 2021 and 2022. So we still have another 2 or more years of Ulysses to go. We're currently getting ready for the first data release, including not just data, but tools for inspecting and analyzing the data. And our Office of Public Outreach is developing materials to bring Ulysses to the public and to disseminate our results to astronomers as well. And just to conclude, we're very excited about making this new resource available to astronomers, but also to astronomy enthusiasts like yourself around the world. Thanks.
Thank you, Will. That was wonderful. It's an intense overview of what you have to do to not only understand all of the background behind ultraviolet spectroscopy, but the intense detail you've got to get to accomplish a project like this. This is one of Hubble's largest programs ever, right?
Yes. Yeah, 1,000 orbits is a pretty huge investment.
I mean, Candles was like 900 orbits, right? And so this is, and I thought that was just amazing that they got that much time for Candles. So we had a couple questions online on this, but I wanted to take as the host, be able to ask you the first question was, you talked about you made the great point when looking at the cosmic reef that, Hubble does imaging and it does spectra. And we've usually said in the Office of Public Outreach that, about half of Hubble's observations are images and about half are spectra. Do you have any details on that, whether that's correct?
I don't know the exact breakdown. I think it might be a little bit more weighted toward imaging. But we certainly, the spectroscopy requires a lot of calibration effort, and I think all the instrument teams are working about equally hard on the data that come in.
Right. But I mean, it's really important for the public to understand just how much information we get from spectra, and that it's equal in partnership to imaging. I mean, everyone pays attention to the beautiful images, but the information that you gleaned, which you talked about so nicely, is really wonderful. All right, so now let's bring in Grant Justice. And Grant has been monitoring the chat online, and he will be able to, I assume he has picked out a bunch of the most interesting questions to ask us. Grant?
Hello, yes. We've actually had the chat's been very good today. We answered a lot of the questions ahead of time. However, I picked up a couple good ones that I reserved before we sicked Frank and I on them. So, all right. So, have any of the findings from the LHC changed the essentials of astral spectroscopy?
The LHC, the Large Hadron Collider?
Yeah. So when you're what I took from this question was when you're searching for elements, when you are looking at spectroscopy, are you searching for any elements outside of your major ones? Do you look for trace metals? Do you look for that sort of thing? And if there were, like, what this person is asking is, are you looking for any of the man-made or anything out of the ordinary, like not oxygen, not hydrogen, not helium?
There are, especially in the most evolved stars, there are elements that are pretty rare in the universe. So people who are studying like red supergiant stars and their winds will detect elements in trace quantities that we find just in trace amounts here on Earth as well. So it kind of it's starting to get deeper into the periodic table, maybe not into those bottom rows of things that we know exclusively to be man-made.
And let me just note for a historical thing is that the element helium was discovered in the sun's spectrum before we discovered here on Earth. So yeah, we have looked into the spectra of stars and seen elements that we didn't recognize, and that's why it's called helium, helios, meaning the sun, and that we discovered that before we had found it here on Earth. And I'm getting a note from Thomas. Will, can you stop your screen share so we can bring the
Sure.
videos up? Okay.
I was just about to say that. Oh, it looks like I got what Trevor wanted to ask. So hey, there we go.
Trying to. Am I still sharing?
Yeah, you have to go to
You
the
are.
Zoom thing and hit the stop, or at the top where it says stop screen sharing.
That seems to have disappeared.
Do you see?
Oh wait, there we go.
There we go.
All right.
Cool. Okay, so I have a follow-up question here. So going back to the graph, there are quite a few people who wanted you to expand a bit more on the actual spectrum that you had up in one of your slides, but how do you know if the black lines that you see that are they caused by something in the telescope's trajectory, or are they caused by atmosphere or something at the end point? How can you tell the difference in something that's on the way and something that's at the destination or the focal point?
That can be tricky. If we're looking at a new type of object, there might be some debate sometimes as to whether something in the spectrum comes from a star itself or something in space along the way. But we've also come to know that certain things are going to happen at certain wavelengths routinely. For example, I talked a lot about those different hydrogen lines. In ultraviolet spectroscopy, there's a hydrogen line. It's got a wavelength of about 1200 angstroms. It happens to be about the same size as one of these coronaviruses, as chance would have it. But this hydrogen line is also very bright in the Earth's atmosphere. So it's tricky to observe this particular hydrogen line in UV spectra because we have this contribution from the atmosphere. Or in the infrared, for example, we have a lot of absorption lines due to water in the Earth's atmosphere. So these are things that we see repeatedly going back years looking at anything in space, and we start to understand what Earth's atmosphere contributes. And we come up with various clever ways to remove that so we can see our signal from the sky better.
Okay, Grant, we have another question from online.
Yep. This is actually an interesting one. So I'm going to take this and go a different route with it, though.
Yes, we do have to edit the questions.
Yes. How narrow of a band, like what kind of resolution can you actually get out of spectroscopy down to individual elements? Can you get down further than that? Can you tell like isotopes? How and what is holding us back from that right now?
Well, this is really common in like the astronomy that people are doing with ALMA, the millimeter array, where you can see kind of normal carbon monoxide. It's not like a huge component of protoplanetary disks, but it gives a strong spectral signature. So people often study carbon monoxide, but then you can have other isotopes, like instead of regular carbon, you'll have a carbon with a molecular weight of 13, so a slightly heavier version of carbon paired with oxygen. And that gives you a line at a slightly different part of the spectrum. So in a lot of cases, that's pretty well understood, and we can look at these different isotope signatures to learn something about temperature and density that you wouldn't have with just a single spectral line.
All right, so Will, you mentioned that this is a legacy program of Hubble, and that, I'm not sure the public truly understands that it comes to ultraviolet observations, Hubble really is the, you have to be in space, and Hubble is the biggest game in town. How far into the future do we have to look after Hubble unfortunately will go away? How far in the future do we have to look to find another ultraviolet observation capability in space?
Well, astronomers have a process for kind of getting together as a community and deciding what kinds of missions they want. And part of the process right now is that there are, I think, 4 large telescope missions being advocated by different community members. And there's a process by which a decision will be made to maybe fund a fraction of those or just one of them. One of the ideas is called LUVOIR. It's the Large Ultraviolet Optical and IR Telescope. I don't think it's a real French word, but it kind of sounds like one. And,
we're excited about it either way. So
right, and it's going to be a much larger version of Hubble, basically. And the idea is that this would be advocated for in what we call the decadal survey that's being put together now-ish. And people talk about, it being the telescope of the 2030s. So, optimistically, maybe 2035 is when something like this might get launched. So it's looking to be a while.
So I guess that truly emphasizes the legacy aspect of this amazing project you're working on here.
Right.
Yeah.
And
well,
in addition to the Hubble lifetime, we on COS are constantly coming up with strategies to make the COS detectors last as long as possible as well. So we kind of think of it as our goal to make COS last at least as long as Hubble does.
It's a lofty goal, though.
All right, Grant, is that it for the questions?
That's it for the questions. I would say, though, if you wouldn't mind, just for the audience, because this was all about Ulysses from the beginning, why don't you just give them a short, 1 or 2 sentence, what Ulysses is to the Hubble project, to Hubble, to STSCI? Because we talked about everything all up here. I want to bring it back to Ulysses.
Well, for me, it's been a great opportunity to work with people all across the Institute. I mean, just my work with COS, it's a team of maybe about 15 of us, but with Ulysses, we've got the STIS team involved. We have people from the MAST archive that archives all the Hubble data, engineers, scientists, technicians, outreach staff. And it's really been great to have all that camaraderie, even though we're all working from disparate locations across Baltimore and the greater, suburban Maryland area. So, for me, that's the best thing about it.
And one of the things I love about projects like this is that the community input that you've gotten on this, that it's not just, STSCI coming up with the ideas, it's, bringing it out to the whole astronomical community, and they get to participate in this. All right, so Will, we want to thank you again, and you're getting tons of virtual applause online. I want to thank everyone for joining us. We will be back next month on October 6th, and you got to come join us because, you got these great projects here with Hubble, but the next Wide Field Infrared Space Telescope will be called the Roman Space Telescope, and you will hear about it from some experts. We're having a conference here at, well, actually, I guess a virtual conference at Space Telescope, and they've just selected 2 great experts to come talk to you about the Roman Space Telescope. We'll see you then. Thank you, and have a great day.